Hello, everyone. Thank you for joining. This is our ninth talk for the year. And today we have Dr. Jonathan Kariv, and he is a data scientist at Izazi Consulting in Johannesburg. And he holds a BSc and a BSc honors degree in mathematics and mathematical statistics from the University of the Witwatersrand. And he got his PhD in mathematics at the University of Pennsylvania. So he's always also now the coordinator or head organizer of the WITS math competition. So he's still doing work at the Witwatersrand. So yes, thank you very much, John, for being here. And yes, you can start whenever you're ready. We look forward to it.
Thanks for having me. I'm going to talk about optimal colorings. If anyone has any questions, please feel free to interrupt and ask. I prefer that kind of discussion feeling. So I guess let me start. So first we're going to talk about Ramsey numbers. There's a whole area of mathematics around this. So we'll start with the warm-up problem, which I'm sure most of you know, which is this one. You've got 6 people, they're at a party, some shake hands, some don't. Okay, another way to say this is you've got 6 points, 6 dots, and you draw a line between each of them, you color them blue or red, and you ask, do you have to have 3 people who all shook hands? That's like a blue triangle, or a red triangle, 3 people who didn't shake hands. Okay, so are you forced to have one or the other? Okay, you don't have to have a blue triangle. You could just have everything red, but then you've got a lot of red triangles. Okay, so does it have to be one or the other? Okay, and the answer turns out to be yes. What you do is you say, let's look at Bob, one of the people. Okay, Bob, there are 5 people. You shook hands with some of them. Well, either you shook hands with 3, or there are 3 who you didn't shake hands with. Okay, that's pigeonhole principle. Okay, but one of those 2 has to be true. Let's say you shook hands with 3 of them. Well, did those 3 shake hands with each other? Okay, if any 2 of them did, you and those 2 are a shook hands / blue triangle. If none of them did, those 3 are a red triangle. And similarly, if you chose 3 if the 3 didn't shake hands with, well, either 2 of them didn't shake hands with each other, you've got a triangle with you and those 2, or they all shook hands and you have that. Okay, next question. Well, gee, 6 people forces it. How about 5? Okay, and the answer is no. You can construct 5 people and draw red and blue lines between them. I'm just going to interchange red, blue, and shook hands, didn't shake hands without, I'll change context all the time. Okay, and you can draw effectively a pentagram. So put the 5 people on vertices of a pentagon, draw blue lines on the pentagon, and all the internal ones are red, and you have no monochromatic, so single colored triangles. Okay, and what this means is that R33 is 6. Okay, so 6 is the smallest number that forces it. Okay, if I've got 7, 8, 9, 10, just pick 6 of them. Okay, so 6 people guaranteed to either have a blue triangle or a red triangle. Okay, 3 or 3. And we can extend this. We can have R333 is, add in a 3rd color, green. So they either shake hands or fist bump or don't do anything. But you now have 3 colors. Or you can say R44. Well, I've got 4 people who all shook hands, or 4 people who didn't. We can do R433. That's 4 people who all shook hands, or 3 who didn't. Okay, so that's asymmetrical. And generally for A blues, or A people who've all connections between them are blue, or B people who all connections are red, or C people all connections are green, or D people all connections are yellow. Okay, and we can phrase this in the language of greetings, and you can add as many parameters as you want. Okay, so the non-obvious question is, do these things even always exist? Okay, Ramsey's big result was, yeah, all of them exist and are always finite, but at some point you actually are forced to get this kind of structure in chaos, no matter how you set it up. Okay, no matter how cleverly you color. Okay, Ramsey died without knowing too many of these values explicitly. Okay, they're hard to prove. Oh, and this should have been a whole bunch of different ones. So here's the idea of his proof. Suppose I want either A, blue, or B, red. Okay, well, pick one guy, this one, and have this many A minus 1 blues or B minus 1, or sorry, either R A minus 1B or R B minus 1A. And you look at this guy, you say, okay, you've got RA minus 1B plus RA B minus 1 neighbors. You've either got this many who are all red or this many who are all blue. And one way or the other, you're going to get that subset filling in. Okay, now if you have more colors, actions, parameters, etc., the sum gets a bit longer, but the same idea holds. Okay, and that's how we prove it's finite, and that's kind of all we have. Okay, so R44 is 18. That was shown in 1979. Okay, and Ramsey died without knowing that fact. Okay, and you then construct it for, 17 and okay, McKay and I'm going to mispronounce this, Radzizowski. Okay, in 1995, they proved R45 is 25. Things are open beyond that. Okay, so Udos, one of my favorite mathematicians, he gave this quote, which is saying, look, if aliens come and say, tell us what R55 is, we can get everyone together in a year, we can probably do it. Okay, that's, Udos died in 96, so maybe he's talking about with 1990s technology. We've got a lot more now, it's not going to make much difference. We could work out R55 with enough firepower. If they ask for R66, we have absolutely no chance. We should just attack the aliens. They're obviously far more technologically advanced than us. We're probably not going to get very far, but we've got absolutely no chance on R66. We might as well try and nuke them. See if it works. It's probably not going to, but it's more likely to than actually trying to work this out. Okay, so now if you're a researcher in this area, yeah, you probably can't work out R55. If anyone does, congrats and let me know and I'll check the proof and totally won't steal it. Okay, so what can we do? Like, what do you work on? Well, you can look at other structures. Okay, graphs are interesting, but once you have the idea, yeah, let me color things, and some structure's going to have to appear. You can get quite a lot of stuff in there. So the most famous example, Terry Tao and Ben Green, 2006, proved that arithmetic series of primes can be infinitely long. Okay. Now, mostly they use results about density of primes. Okay, so nothing, or not a lot, about the particulars of where primes are. Okay, that's notoriously hard to say things about the structure of primes and where they appear, which is why this was sort of the result that Towles-Field's middle was most associated to. Granted, he had, so many other results that, well, that's why he got it and Green didn't. Okay, but the fact that you can prove this thing about primes is one of the big results of, the last 20 years. Okay, now what does this have to do with colorings? Well, color the primes red and the composites blue. And this result, not quite, but more or less says, look, if you have a set of numbers with roughly the density of the primes, provided, some really weird edge cases don't occur, you're going to have a monochromatic sequence, in fact, a red sequence of as any length you like. Okay, so again, we have a coloring, just primes and composites as our two colors. And we have a structure, long arithmetic progressions. Okay, so this actually looks quite a lot like Ramsey theory, if you think of it that way. So here's another example. Consider the integers mod n. Okay, if you haven't seen modular arithmetic, put n people in a circle. Okay, and color each person or each integer blue or red. Okay, if you want to think of this as n people in a circle, you put blue or red hats on each head. Okay, and we're going to try to minimize the number of monochromatic arithmetic progressions of length exactly k. Okay, now if n is prime and k equals 3, it turns out that the number of monochrome formations only depends on the blue-red fraction. Okay, you expect, well, if you have k of n, well, no, we're using k for 3 for the progression length. If you've got b over n blues and r over n reds, you're going to get b cubed over n cubed plus r cubed over n cubed, total progressions. It doesn't need to be true that, it does not need to be true that the number of blue progressions is b cubed or is b over n all cubed, but the sum of the blues and the reds does have to do that. Okay, so what about k equals 4? Oh, and for k equals 3, start with any color you like. The next one's got about a 50% chance of being the same, and the one after that's also got about a 50% chance. So if you just set the blues and reds equal, you get a quarter. Okay, a quarter of those monochromatic progressions are going to be, a quarter of arithmetic progressions will be monochromatic. And this means that, well, if you set it to a half, that's the minimum. So can we do that? Can we do any better with k equals 4? Okay, k equals 3, we can't. Well, 2010 Wolf showed that, yes, you can get a little bit, just a tiny little bit less than an eighth. Okay, and that seems like a kind of obvious result. Color randomly, you'll get an eighth on average. You can't do any better than that. You expect to be able to do better than that. But with k equals 3, you can't. So this is actually quite a big result. Okay, now Ping and Liu, just 2 years ago, with a couple of intermediate results, got things down to 7/96, 2 out of 33. Okay, that's a little bit less than a quarter. Sorry, no, that's a little less than a 16th. That's a little more, but a 16th is a lot smaller than an 1/8. So this is really pushing things a lot. Okay, I mean, look how close this is to the average. And you can see really that it is quite a big result. Okay, and there's also work on optimal 2 colorings for n. So by this I mean the first n integers. Just 1, 2, 3, 4 up to n. You want to minimize the number of colorings. Okay, Ping and Liu also did a lot on this. So I'm going to talk about some work with some friends, Torrin Greenwood, who's at North Dakota State University, and Noah Williams, who's at Appalachian State University, both in the US. So, they meet in their workday, and because I work in industry, after work I go talk to them, and so time zones are great. Yeah. Okay, so we sort of put this on its head, and well, not really on its head, but instead, okay, you're talking about n discrete points, 1 through n. We're just going to look at the unit interval. Okay, so color every real number, blue or red, between 0 and 1. And we're going to ask, what fraction of monochrome progressions do you need? Okay, so you need to make that a little bit precise. So we assume that the colorings are measurable sets. So, the blue has to have a fixed measure. So does the red. Okay, if you don't have this, well, the axiom of choice makes weird things happen. Right, so you can probably get, that measure 1 is blue and red, or if you allow the axiom of choice, all kinds of weird things happen. The axiom of choice happens when you have non-measurable sets. Those two are linked. Those two ideas are linked. So we're just going to talk about measurable sets of blue, equivalently measurable sets of blue. Equivalently measurable sets of red. And we're trying to minimize things. Minimize the number of arithmetic progressions of length 3. Okay, well, first result, we can cover this with intervals. And that can get almost as good as measurable sets. How do we know this? Well, you look at the definition of a measurable set, and it's effectively saying it's a union of intervals. Okay, well, we can get arbitrarily close to that with a finite bunch of intervals. Okay, so this feels a little bit not so helpful. I mean, there's a hell of a lot of intervals. Okay, well, you can actually go to uniform intervals because, the only thing that matters is the endpoints, and you can get really, really close to them with rationals. So you can evenly split it up into a bunch of blues and reds. Well, there's still a bunch of those. In fact, largely infinitely many. But we can do a little better. We can say, okay, if you give me a coloring with uniformly spaced intervals, so it's from I over n to I plus 1 over n, is all the same color, we have a way that's quick enough to compute how many, or rather the measure of how much what fraction of the progressions are monochrome. Okay, so the idea is you start at one of the intervals, you jump k blocks, or t blocks, let's say, and then you jump about t more blocks, right? Because it's an arithmetic progression, the jumps are the same size. You just worry, do you cross a boundary the second time? Turns out you can, but you can only do it once. So you say, okay, the actual arithmetic, the arithmetic progressions as on the intervals, think of them almost as discrete points. Those count. And the almost arithmetic progression, so if you jump t, and then you jump either t minus 1 or t plus 1, those count half as much. And that's all you have to think about. Your computer can. And so click run a genetic algorithm and you'll find a pretty good coloring. Fortunately for us, we keep getting the same coloring and we conjecture it's optimal. Okay, now exact results in Ramsey theory, as we spoke about a while ago, are pretty rare. So, we're quite chuffed about that. Problem is proving this is actually optimal is hard. So here is the coloring. Isn't it beautiful? Okay, so red, you've got 6 red intervals locked in with 6 blue intervals. Okay, and if we put the first thing on the x-axis and the third, final thing on the y-axis, we can actually plot it. Can you get this quite nice picture? Okay, now as I vary where these cutoffs are, these shapes are going to change. Okay, that actually gives me a function for the number of monochrome progressions. Okay, which turns out to be just a quadratic. Okay, with quadratic in x0, x1 is the first cutoff, x2, x3. So it's in 12 variables.
Sorry, can you maybe explain that plot? I'm not quite following what it represents.
Oh, sure. So we have the coloring on the x-axis. And we're trying to count arithmetic progressions by saying, look, first thing is 0.7. That's on the x-axis. Last thing maybe is 0.5. That'll make the second one 0.6. Okay, but if I know the first and the third term, okay, the midpoint of that is the second term. I know it's 3 I'm talking about. Does that help?
A bit. I'm not quite there yet, but I think I have a clue of what's going on. Yes.
Okay. Okay. And yeah, this is, I think, Torrent's mouse in this image. Sorry. Okay, so this square, for example, is the arithmetic progressions that lie entirely in here. Okay, and these lines that you see over here are the times where the middle term changes color, or disappears, rather. Okay, so the area of these shapes is almost a quadratic in the endpoints. Well, I say almost because at some point a shape disappears or another shape appears. So it turns out it's piecewise quadratic. Okay, so the first good news is you can calculate these endpoints exactly. Right? Because any small variations are still quadratic, we're okay. Okay, so that's the first thing. And the second thing is we can actually enumerate all possible shape configurations. Okay, let me just go back a little bit. So we said, look, we keep getting this configuration. We will be able to show that among all 12 interval configurations, it's optimal with a lot of computer power. Okay, we can't show it's actually optimal, but we can do it for 12 interval colorings. Well, for 12 interval symmetric colorings. Okay, and would be nice to show that symmetry somehow always wins. It does seem to. Okay, so quadratic formula, and you'd have to optimize on for each subinterval. So now it becomes a question of enumerating the subintervals. Okay, well, now we can ask, where does this picture change? Okay, and it turns out that it changes when two of the x's, say x3 and x8, equal twice the middle. That turns out to be where the shape changes, or twice another endpoint. So xi plus xk equal to 2xj. Okay, so we only really need to ask ourselves xi plus xk, between which double of an xj does it fall? Okay, and what we did is try to see which configurations are possible by adding a constraint at a time. And if you've got sort of x2 plus x7, well, it's either between 2x2 and 2x3, 2x3 and 2x4, 2x4 and 2x5, 2x5 and 2x6, or 2x6 and 2x7. So you get your computer to list those and run a linear programming to see if there's a place where that could be the case for each of those. Some it won't. You can throw those out, great. Some it will. You add that to this ever-growing list. And for each of these, you get a quadratic. And then the computer can just figure out, it's a calculus 1 problem, right? Just where do I put these things to optimize? So we have a computer program running. It's almost done. And then you look over all these intervals and say, gee, which of those was the best, subinterval? Yeah. So we're running through it. It looks like the one we found actually is the best. And we might even be able to run it for 14 subintervals instead of 12. Now this leaves a few problems open. Okay, so like in Ramsey theory, or like in the graph theoretic version of Ramsey theory, which we started with, we've been working on R33 or I33, depending on what you want to call it. We want to know what happens with 4.3 and 4.4. We don't. Those problems are open. Same for more colors. So what if we add green? Okay, I've been running a few generic algorithms lately. You get pretty pictures. That's early days. Also, okay, we're using the straight line. We could use the circle. Or when I say the line, I mean the line segment 0, 1. Okay, what if we put a broken line with like a hole in the middle? Does anything change? Well, something changes, but what? And thanks. That's my talk. Are there any questions?
Hi, John. Could you go back to the graph?
Sure.
And so I think so you're plotting arithmetic progressions,
Yeah.
or monochrome ones somehow.
Yes.
So if you're plotting the point xy, what progression would that be?
Oh, so that's the progression x plus y over 2, y.
Okay, so this is specifically for progressions of length 3.
Yeah, we are dealing with progressions of length 3.
Okay, thank you. I think that clears things up a bit.
Yeah, sorry if that wasn't clear. But yeah, we are talking about progressions of length 3. And the question of progressions of length 4 is open and interesting. And so's the progressions of length, red progressions of length 4 or blue progressions of length 3.
Yeah. So would that be sort of R43 or R44 equivalent?
That yeah. And something I didn't mention, but R34 is quite naturally equivalent to R43.
Yeah.
Yeah. So yes, there is that generalization to longer or uneven progressions.
And then one more question. This is sort of more an abstract thing.
Mm-hmm.
I noticed a lot of the work you did is based on computation and making use of computers to sort of fill in the gaps where we can't go through all the cases and whatever ourselves.
Sure.
So how much would you say you sort of rely on computers rather than sort of solving it by hand or whatever?
Right. Then analytic things.
Yes.
Quite a lot. You do need sort of clever algorithms to do this, which you finding those algorithms feels a lot like doing analytic maths.
Yes, I imagine there's a lot to do so that these don't take forever to run.
Right, or even that's a chunk of it. So I think I mentioned the Brzezinski. He got tenure for this result. He got in a computer science department. Not in a maths department. Yeah. So computers do seem to be, a really helpful tool for this stuff.
Yeah. Okay. Cool.
They find nice configurations, and then you try to prove you can't do better. So yeah.
Why the unit interval? Was there any specific reason? Or?
Well, we could have done the interval 0, 2, but you can just shrink it down, right? There's nothing special about it being the unit interval. But
yes, but sort of why rather than sort of, as you said, a circle or some other structure?
Right. Well, so the circle has a lot of we kind of have to start somewhere, I think, is really the answer. So you want to start with something simple. We thought about the circle, but I think there's already some stuff done for the circle. So this when k equals 3 on not the circle but the integers mod n, I'm pretty sure that the same result goes through in the circle. So we figured we wouldn't get anywhere with that. And then that left the unit, or that left a segment. And, having two segments with a hole in the middle, it sort of feels like a later question. Sorry.
So is there any reason this can't be generalized to something two-dimensional or high-dimensional? Is there a reason it must be one-dimensional?
No. You could certainly talk about arithmetic progressions in the square, or the disk, or 7 million dimensional cube. We started with this because it seemed sort of like the most, well, I guess the easiest case. I mean, yeah, all these generalizations are out there. Anyone who feels like working with me on this, give me a shout. Completely happy to. But yeah, all of the stuff can be generalized in that way.
John, how much in a week do you spend? How much time do you spend on this?
So we meet for a couple of hours, and then sometimes we're either writing, doing lit review, or writing things up, or writing code and letting the code run. Probably sort of 4 or 5 hours a week at this stage.
Oh, okay, that's very cool. But I guess you spend a lot of time on just, you formalize some idea maybe, and then you have to write code for it, because otherwise you can't see the results.
Yeah, there's a lot of that.
Do the two other colleagues also write the code? What is their specialities?
Yeah, so they're both combinatorists as well, or probabilists. Sorry. Let's see. So, it depends who has what idea. Like, I had the idea for let's run this generic algorithm. Torin figured out how to do the adding constraints to the linear programming one at a time, and then getting something feasible. That's kind of how this works. If you have something, if you have an idea and you try code it up, or you explain it to the group and someone else goes, "Oh, I see what you're doing."
Yeah,
that's why it's wrong.
Yeah. That's very cool. And would you describe your group to be the optimal size?
Oof, that's a tough question. I think 3 or 4 people is helpful. I think when you're working on maths or industry projects, I think it's sort of the social dynamic is almost as important as the size of the group, or more.
Yes.
Like, as long as everyone's getting along with everyone, things are
good.
good.
There has to be almost not companionship, but otherwise you're not kind of growing in your work and moving efficient.
Yeah, but I mean, I had another project where there were 8 of us.
Oh, okay.
But it was kind of me and 2 other friends, and then another group that there were 3 of them that did stuff, and then we kind of stuck stuff together.
It's still kind of the small groups, but you have a bigger group that the whole project.
Yeah, but I mean, we all kind of worked on writing it up together.
Yes.
And things went very smoothly then.
Okay.
Yeah, mathematicians tend to get along quite well with each other, so that's helpful.
Right, so if there's any more questions, please ask. Otherwise, I will conclude the meeting shortly.